Okay, well, here we are at the beginning of Chapter 3. Chapter 3 is called Molecules, Compounds, and Chemical Equations. This is an abbreviation for equation that is very common in chemistry, so you might see it from time to time, so now you know what it means. The first section that we're going to cover in any detail is actually the second section, 3.2, which is about chemical bonding. 3.1 is actually a section that's dedicated to kind of demonstrating the kind of changes in properties that can occur when chemical bonding occurs. And so, first of all, formation of bonds between atoms can actually change the properties of the elements involved in the bonding quite a bit. And the example the book uses is water, where you have hydrogen, a gas that is explosive, potentially, and oxygen, another gas which vigorously supports combustion or burning of stuff. And when you combine them together in a ratio of 2 to 1 through chemical bonds, what you get is a liquid that can put out fires. And so that is a pretty huge change in properties just because you've taken some atoms and bonded them together. And so the result of this is properties of compounds are often very different from the properties of the elements in them. Maybe not always the case, but very frequently. Okay, so first some basic definitions to sort of set the groundwork for what we're going to go on and do later. Some of these definitions are basic enough that we may have mentioned them before, but it's worth mentioning them more than once. Molecule is just two or more atoms chemically bonded together. For a molecule, those atoms can be of the same element. And a good example of a molecule where both of the atoms involved are of the same element would be oxygen. Oxygen is what's known as a diatomic element, meaning that in nature it's always found in pairs. So you won't find individual oxygen atoms in nature. And in fact, it's so common to find them in pairs that when we say oxygen, we are generally understood to mean O2 molecules. If we mean individual atoms of oxygen, we normally say oxygen atoms. And so that is a molecule, but it's also an element. Even though oxygen is normally found in pairs like this, remember that actually the data in the periodic table refer to each atom of oxygen. So if you want to say the mass of O2, you have to take the mass in the periodic table and double it. A compound is two or more atoms of different elements chemically bonded together. So they do have to be different elements in order to be a compound. So, for example, H2O, water, or CO2, carbon dioxide, those are compounds because each of them involves at least two different elements. Also, of course, since bonding is the point of the entire chapter, we might want to check in on what's a chemical bond. Turns out there are two major kinds of chemical bonds. One involves transfer of electrons from one atom to another. The other involves sharing of electrons between two atoms. So transfer or sharing between two atoms. And it has the effect of holding the atoms together. There are a couple of types of, as I said, there are two types of chemical bonds. An ionic bond is a transfer of one or more electrons from a metal to a nonmetal. Because remember, as we said before, when forming ions, metals tend to lose electrons and form positively charged ions, and nonmetals tend to gain electrons to form negatively charged ions. And so what happens here is the metal loses one or more electrons to form a positively charged ion. And the nonmetal gains one or more electrons to form a negatively charged ion. And the positive ion and the negative ion, because they have opposite charges, they're now attracted to each other. And that attraction is known as an ionic bond. In most cases, the electrons that the metal loses are the same electrons as the ones that the nonmetal gains. So the electron is actually, or the metal is not actually going to lose any of its electrons until the nonmetal is there and ready to take them in. And obviously the metal can't gain, or the nonmetal can't gain any electrons unless there's something around that's willing to give some electrons up. An example of an actual electron or ionic bond can be found, for instance, with sodium. As we saw before, sodium tends to form positive ions by releasing one electron. If there's a chlorine in the vicinity, it will take in that same electron and become a chloride ion. And now you have Na plus being attracted to Cl minus, which is sodium chloride. And actually, ionic bonds are not directional, meaning that, say, a positive ion will be attracted to several different negative ions at the same time. And vice versa, a negative ion will be attracted to several different positive ions at the same time. The result is that ionic solids are made up of a 3D array of alternating positive and negative ions. And it just repeats on and on and on again in 3 dimensions. And it turns out that for sodium chloride, the overall ratio is 1:1, and that's why it has the formula NaCl. Because compounds like that, ionic compounds, exist in this 3-dimensional array, it's not actually ever likely that you would ever have one single sodium ion and one single chloride ion bonded to each other and not bonded to anything else. So in order to give the actual molecular formula of an actual grain of salt, you would have to give, if we were doing it as a molecular formula, you would have to give the number of sodium ions and the number of chloride ions, each of which could be in the quadrillions or more, even for the tiniest little grain of salt. But the thing is, they would, whatever those numbers are, they would always be the same. And so for ionic compounds, we boil it down to the lowest whole number ratio of positive ions to negative ions. And so for sodium chloride, it's 1:1, so we just call it NaCl. If you were to look at a piece of NaCl, it would look something like this. You'd have a sodium ion and a chloride ion, and then another sodium ion, and then another chloride ion, and then another sodium ion, and then another chloride ion, and so on and so on and so on and on and on. But this sodium ion would also be attracted to other chloride ions around it. And this chloride ion would be attracted to more sodium ions. And so on and so on and so on. And it goes on in 3 dimensions, so it goes back into the paper as well. And on and on and on. And now, if we total up the number of sodium ions and the number of chloride ions, let's see what happens. For sodium, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And for chloride ions, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so see, basically it goes on and on like this. So however many sodium ions you got, that's how many chloride ions you've got. So we bring it down to the lowest whole number ratio and end up with NaCl. Okay, covalent bonds. For covalent bonds, they are the sharing of 2 electrons between nonmetal atoms. In this case, the electrons are not actually transferred from one atom to another because nonmetals tend to have an attraction for electrons that are fairly similar to each other. If you're in a situation with an ionic bond and you're reacting a metal and a nonmetal, well, the nonmetal has a very, very strong attraction for electrons, and the metal doesn't. The metal, in fact, lets its electrons go pretty easily. So in that case, the nonmetal usually has enough strength to pull electrons right away from the metal. In a case like molecular type compounds, you're reacting nonmetals with other nonmetals, and there may be a difference in the attraction for electrons between them, between the 2 atoms, but the difference is usually not that great. It's not great enough for one atom to tear the electrons right away from the other atom, so they end up having to share them. It's often an unequal sharing where the electrons will remain closer to one of the atoms than to the other one, but still, it's still a sharing, and the electrons will normally be found between the nuclei of the 2 atoms. Okay. So the electrons go around both nuclei. And that's what helps hold them together. And the result of this would be what are known as molecular compounds, and they consist of basically separate individual molecules with the same ratio of elements in each unit. A good example of that would be H2O. H2O consists of a bunch of separate little particles, each of which has 2 hydrogens and 1 oxygen in it, and those are known as molecules. So ionic compounds don't actually exist as molecules. Sometimes we use the phrase molecule to reference something like NaCl, but technically it should actually be called a formula unit rather than a molecule, because ionic compounds, like I said, don't actually exist as molecules. Okay, so 3.3 is about representing compounds, chemical formulas, and molecular models. So ways of conveying what the makeup of a molecule is. And what the chemical formula is just a shorthand way to convey what elements are present and in what ratios in each unit of the compound. Okay, so basically, how many atoms of which elements are in each unit of the compound? In the case of covalent or molecular compounds, the formula actually gives the composition of each molecule. Okay, so H2O, CO2, some big molecules like glucose. So each unit, each molecule of glucose has in it 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Okay. So for ionic compounds, on the other hand, the formula is actually the lowest whole number ratio of positive to negative ions. Like we saw with sodium chloride. You may have even the smallest piece of sodium, like I said, is probably going to have billions or trillions or quadrillions even of sodium ions, but it'll have the same number of chloride ions. So we reduce that to a 1-to-1 ratio, NaCl. For calcium chloride, again, it's a 3-dimensional network. Only this time, there are 2 chloride ions for every calcium ion. So even the smallest chunk of calcium chloride you can come up with would probably have billions and billions of calcium ions, and it would always have twice as many chloride ions. So we boil that down to CaCl2. For a formula for a compound, there also arises the question of in what order do you list the elements? Why is water H2O instead of OH2? Why is carbon dioxide CO2 instead of O2C? You know, could you write it either way? Could you write sodium chloride as ClNa? Well, actually, the answer is no. There are tens of millions of compounds out there that are known, and there are more being synthesized or discovered from nature every day. And so in order to keep things orderly and to sort of facilitate knowing what other chemists are talking about, there is a certain order to the way that the elements should be listed, both in the formula and in the name of a compound. And so a formula, or name for that matter, usually lists the more metallic element first. And the other one last. Now, when we say more metallic, what we mean is that the element in the compound that acts more like a metal. Or in other words, the one that acts less like a non-metal. What metals like to do is lose electrons to become cations. What nonmetals like to do is gain electrons to become anions. So essentially what we're saying is whichever element is more likely to lose electrons and less likely to gain electrons, that's the one that goes first. And as of the knowledge that we have right now, all we can really say to decide which element in a compound is more metallic is that, notice where the metals tend to be in the periodic table. They're over on the left-hand side and even on the right-hand side, but they're down toward the bottom. So generally speaking, the further to the left an element is in the periodic table, the more metallic it is. And also the lower down in the periodic table, the more metallic it is. And more metallic, of course, is a comparative term. So it's possible to compare nonmetals for, say, metallic character. So if you look in the periodic table, if you look down, say, group 7A, where we have fluorine, chlorine, bromine, and iodine, those are all nonmetals. But looking down the list, the ones toward the bottom are more metallic and therefore less non-metallic than the ones at the top. So in this list, if you had a compound between, say, iodine and fluorine, the iodine is further down, so the iodine would be considered more metallic, and that would go first in the formula. And fluorine would go second. Because it's on top, it's less metallic. And at this point, there probably aren't going to be too many cases in which you have to decide what order the elements should go in. But just in case, that's how you do it. Okay. Okay. So there are different types of chemical formulas. Depending on what it is you want to convey. One is known as the empirical formula. One is known as the molecular formula. And there's another type that's known as structural formula. So to get into those, the empirical formula is called empirical because the word empirical implies that something comes from experiment. Something that's empirical comes from experiment, and the empirical formula is called that because the empirical formula is often the result of some sort of chemical and experimental analysis. The empirical formula is a statement of the lowest whole number ratio of the elements present in a compound. If that sounds familiar, it's because that's what we just said was the formula for an ionic compound. The formula for an ionic compound always gives the lowest whole number ratio of the elements present in a compound. So it turns out actually ionic compounds are always given as the empirical formula. So ionic compounds always use the empirical formula. Molecular compounds, on the other hand, don't always use the empirical formula, but they do sometimes. In a molecular compound, the molecular formula, which tells you what's actually present in each molecule of the compound, is a whole number multiple of the empirical formula. But keeping in mind that that whole number can be 1. So in other words, the empirical and molecular formulas sometimes are the same. Okay, so, or different, depending. So for instance, say the molecular formula for something like H2O. Well, actually, it turns out that 2 to 1 is the lowest whole number ratio of those two elements as possible. So the empirical formula for H2O is the same. For CO2, again, 1 to 2 is the lowest whole number ratio possible. So the empirical formula for CO2 is CO2. But how about something like hydrogen peroxide, H2O2? Both of those subscripts are divisible by 2. So to get the empirical formula, that's what you do. Divide them by 2, and you get HO. That's the empirical formula for hydrogen peroxide. And I mentioned the formula for glucose. It's also the formula for several other sugars a few minutes ago. It's C6H12O6. You might notice that all of those subscripts are divisible not only by 2, but they're also divisible by 3 and by 6. And so in order to go from the molecular to empirical formula, what you want to do is divide the subscripts by the largest factor possible so that you get the lowest whole number ratio of one thing to another. So dividing each of these subscripts by 6, you get CH2O. That would be the empirical formula for glucose and the other sugars with 6 carbons. Okay, molecular formula then is a representation of what's actually present in each separate molecule of the compound. And keep in mind that the molecular formula is always a whole number multiple of the empirical formula. In fact, up here, we could even list the multiples. In a case where the molecular and empirical formulas are the same, of course, that means that the multiple is 1. But in this case, the molecular formula is twice the empirical formula. And in this case, the molecular formula is actually 6 times the empirical formula. But they're all whole numbers. Okay, and then structural formulas. Structural formulas are useful because what they do is they show the relative arrangement of atoms in a compound. Or in other words, what is bonded to what within the compound. Because structural formulas actually show the bonds. If you have just a formula like even H2O, I mean, you know, off the top of your head, just looking at that formula, how do you know what's bonded to what in that molecule? Is the oxygen in the middle with 1 hydrogen on each side? Actually, that's it. But you don't know by looking at it. It could be hydrogen, hydrogen, oxygen. Or, you know, I think that's probably about the only 2 possibilities. But something like C6H12O6, there's actually several possibilities for how you could arrange those atoms. And that's even assuming that you know the rules on how many bonds each element forms. Because actually it turns out there are actually several compounds that have the formula C6H12O6. Glucose and fructose are probably the best known examples. And the only difference between the two is not what's in each molecule, but how those atoms are arranged. So a structural formula would actually allow you to distinguish between glucose, which has this chemical formula, and fructose, which also has this chemical formula. So that's one of the useful things about structural formulas. And generally, structural formulas will use a line for each bond. And a single line will represent a single bond. And a single bond just means that the atoms are sharing a pair of electrons. And a double line represents a double bond. And what that means is that the 2 atoms are sharing a total of 4 electrons. And you can have a triple bond too. A triple line represents a triple bond, and that means that the two atoms are sharing a total of 3 pairs of electrons. Now, it's possible that a structural formula may or may not give the correct shape of the molecule, but it generally does at least give you the information to figure out what the shape of the molecule is. As I said, for H2O, actually the oxygen is in the middle and the hydrogens are on either side. You can draw that like this, or if you want to represent more what the molecule really looks like, you would draw it bent like this. But we won't see why that is until later in the semester, but I'm just showing you that a structural formula may or may not give you the actual shape of the molecule. But it does, either way, show you what is bonded to what. Carbon dioxide, on the other hand, really is a linear molecule. It's not bent at an angle like water is. Carbon, though, is attached to each oxygen with a double bond, and that's what the double line means. And probably the best known compound with a triple bond in it would be acetylene, the gas that's used in like welding torches and things like that. That has a hydrogen single bonded to a carbon, and then that carbon is triple bonded rather to another carbon, and then a hydrogen. This molecule actually also is linear, so this actually does give you the geometry, but that's really mostly by accident rather than intent. Okay, so we got that. Next we look at molecular models. For a moment, but I see we're at the end of this segment, so I'm going to break there and we'll be back in a moment.